In the second part of the PyTorch tutorial, we will now look at how we can actually implement our own neural network and also train it here in PyTorch. To learn it, it's probably the best to actually learn it based on an example. And the example we will use here is the popular XOR. So the exclusive OR assigns basically a data point the label 1 if one of its inputs is 1 and the other one is 0, and otherwise the label is 0. This basically then is very popular because a single perceptron cannot solve this, as it is not a linear classifier which can solve it. And we will use here a very small neural network with a few perceptrons that can actually learn it. So let's maybe get started. And the first thing you have to do in PyTorch is to build your own neural network. And for this, PyTorch provides the package torch.nn, which you can import here, just saying import torch.nn. Mostly you can see that's defined as nn. And in there, we will see most functionalities you actually need to build your own neural network is provided. Additionally, there's also the package torch.nn.functional, which is usually also good to implement or to import. So it's basically very similar to torch.nn, but differs in the way it actually defines these functions. We will see it now and specifically because torch.nn defines, for example, a layer as a module, while torch.nn.functional just provides it as a function. So let's first now look at what is actually a module, because mostly what you use in PyTorch are modules. Modules are also what you have learned in the basically in the lecture as a module. So it can be an activation function, it can be a linear layer, it can be whatever is in the neural network. And in PyTorch, it's very basic to implement this. So you create a new class which inherits nn.module. You have here initializer where you usually then, for example, say these are my parameters, or initialize even submodules if you have some. And then you define here a function which is called forward. And in this forward function, you define the computation you would do in the forward path of a module. And then basically the backpropagation, so the calculation of the gradients, is done automatically. Although you could also do it manually, usually you rely here on the automatic calculation. The forward function has also a different property or additional property, namely if you call a module, so if you create an object of this module and call it, like here, and then with the input x, it actually executes the forward function. So the forward function is really important where you implement your computation. Now let's look at how you would actually implement these small classifier. So what we want to do here is that we have two inputs, as you have seen from our example input. We have then here one layer, mapping it to a hidden layer of neurons, and then one output layer with a single output neuron. We want to have then, for instance, usually you create then a module to support any arbitrary number of hidden units and then pass it as a parameter. So let's do it here below. You can simply say class, again, whatever you want as a name. In our initializer, we first then take the number of inputs as a input here, then the number of hidden units and the number of outputs. Then you see we create one module called nn.linear, which is a linear layer. It basically represents exactly this layer from two inputs to now, in our case, 4 outputs. We have an activation function. Here we use tanh. There are many different, and we will actually look in another tutorial at all the different activation functions. And then we map this hidden output to one single output neuron, which would be then our classifier. See then here we define the linear layers. Inside the linear layers, again, we define automatically the parameters are actually defined. In the forward function, we can just run one layer after another. So we do here sequential of the first linear layer, apply the activation function, the next linear layer, and output. And that is all you have to write in PyTorch to already have your own neural network. We can then create one by just creating something, an object of a class, which is when we say, okay, we want 2 inputs for hidden units, 1 output. And if you print that, you actually see then always in PyTorch all the submodules one has. So this one has a linear layer, as we have seen, 2 inputs, 4 outputs, the activation function, and the second linear layer with 4 inputs and 1 output. It is quite important to also know where the parameters are stored or what parameters actually this neural network has, because this is what you want to learn, right? The weight matrices, biases. In PyTorch, you can access the parameters using dot named parameters or just parameters. And if we do that here, you see that we have 4 parameters. So for each linear layer, we have a weight with a shape, as we know it, 4 outputs, 2 inputs of this layer, a bias, and again, a weight and a bias of the second layer. The activation function here has no parameters because the TON-H is just a function and doesn't have any specific parameters actually. So as you see, that can actually be a bit tedious if you have a lot of linear layers, a lot of activation functions. Therefore, also PyTorch supports to actually define lists, or what they have here, sequential, and then dot sequential, which we will use actually quite a lot in the tutorials. There you can really just specify a list of modules, and these are then directly always executed in the sequence. It's quite helpful. So these things we will see later in the tutorials and so on, where it actually becomes helpful. After now having defined our model, it's time to actually define our data. Therefore, in PyTorch, we also have a package called torch.utils.data, which you can import here. The data package provides 2 classes, or 2 classes in general, which are important for PyTorch. First class is just the simple dataset class. So the dataset class here, data.dataset, is basically where you define your own dataset, what the data points are in it. It has 2 functions, which we can see here below, def_length and def_getItem. The length method is nothing else than should return the number of elements in a dataset, while getItem should return then the ith item of a dataset. So if you have, for example, 10 data points in your dataset, then you should be able to access through this function all the data points from 0 to 9. In our dataset here, I created then a simple one for our XOR example in the initializer here. So it doesn't have any specific structure for the initializer. There I basically just say how many data points we want, what standard deviation we want for the noise. We then generate here simply the labels for the XOR and add the noise. So nothing actually really serious or different. The length method then returns how many points we actually generated, while the getItem, so if we get the index, we just return the data so from the data, the index, and also the label. So you can return here as many points as you want, as many not data points, but basically you can then take input, the second input, the third input, and the labels, what you usually have. So let's also run that. And then we can create a data set down here, just by specifying now here the size, and you see you can actually access this length method and this getItem method as if it would be an array, which is then quite useful and quite intuitive to actually run. Below here, I also just use a function to actually then visualize the data. This is now nothing important because it's actually just NumPy operations, but it just shows you, okay, these are actually the data points we have now stored in the data set, and these are the ones we will use to learn our neural network. The second class in the data package is the data loader, and the data loader is there to actually provide or basically put the data into batches with which you then learn your neural network. It's quite helpful because it supports things like multiprocessing and shuffling and so on. So a lot of things you would normally have to implement yourself to optimize your code, while this is here provided. In general, there are a lot of different functionalities I listed here. When you need it, you can just look it up in the documentation. But the general thing is that you first have to specify the batch size you want to use and if the data set should be shuffled or not. So usually in training, you should shuffle, while for validation and test, you usually don't. So let's create a data loader, and you can access it by just saying here, basically creating an iteration object and saying next, but you usually use it in for loops. For example, for data point label in data loader, we will see later here in the training loop how it's actually used. So this is basically just the access to the first element, so you can check what it actually returns. And you see that it stacks the outputs. So it takes the whole batch, the 8 elements we have defined here, and stacks them. So we have now 2 dimensions, the 8 and 2 input dimensions. And the label is then also stacked into one vector. Therefore, if you train, or if you have a new task you want to do, first define your data set, and then you can just use the data loader class to have an efficient loading of your data. After that, we can now take a closer look at optimization. So we now have data, we now have a module, a network. How can we optimize now the model for the data? In general, there are 5 steps, as you know, which we would have to do. So first we need to get the data from the data loader, which we have seen before. Then we need to obtain the predictions, so run the forward path of a module. Third part is then to calculate the loss, which we'll look at. Fourth, backpropagation, so calculate the gradients to the parameters based on the loss. And 5 is then update of the parameters. So we already know steps 1, 2, and 4, and we'll now look at 3 and 5. So 3 and 5, for the loss calculation, PyTorch again provides a lot of modules. For example, here the binary cross entropy you might already know, which is often used for binary classification. You can, of course, also define your own loss function by just having a couple of tensor operations, because as you know, these are also differentiable, but usually you get, well, you're fine with using just a loss module. And one thing you notice here is that we actually see that we use binary cross entropy with Logit's loss. So what means with Logit? We go back to our module here. For our model up here, you actually see we just predicted one output, but this output can be between -infinity and infinity, right? We do a normal binary classification, we would want to have it between 0 and 1. But if we calculate the loss on 0 and 1, it is less accurate, especially less numerically stable, because you see in the binary cross entropy, we have here logarithms, and it's more efficient and it's more accurate to actually calculate these logarithms in a way on the logits actually, so not directly putting it in the sigmoid function. And this is what PyTorch here provides. So you can use a BCE loss module, or you can use a BCE with Logits loss module. Usually the with Logits is recommended. Next is how do we optimize our model, our parameters based on the loss. As you know, there are a lot of optimizers in deep learning, and PyTorch also provides most of them. They are defined in the package torch.optim, which are then most of the optimizers. Most popular is probably stochastic gradient descent, which nothing else than calculates the gradients for the parameters given the loss, and then just takes a little step towards optimizing this loss. I will not really go into detail what SGD is, because you will see it more detail in the lectures and also in the next tutorial. Our optimizer object provides 2 functions, which are important. First one is optimizer.step. So this one basically takes the gradients of the parameters and updates then the parameters accordingly, so optimizing them towards the direction of minimizing the loss. While the second one is optimizer.zeroGrad. So zeroGrad basically sets all the gradients of all parameters to 0. First, it sounds not really intuitive. Why do we need that? Well, if you call backwards in PyTorch, so do this backpropagation, it actually sums gradients. So if a parameter is twice in a computation graph, you sum the gradients. So that's important. You can't overwrite the gradients based on another one you got. Therefore, with optimizer.zeroGrad, it's important to first clean all your gradients before you do the backward step on the loss. Otherwise, you sum the gradients of all the steps, and it just gets very noisy, and your gradients are not really the gradients you want. Therefore, always remember, first call the zeroGrad, then you can do the backpropagation, and then you can do the step, which we'll see also now. Next step, namely the training. So we now know how to optimize, how to load the data, how to create a neural network. Now let's look at the actual training. So first, we create here again a training data set. I created a little larger one and also a larger batch size. These should be, as we have a tiny neural network, should be also able to run on your CPU. But just basically as also a small test, or basically that you get to know how to use a GPU, we'll push it here also the model to a GPU. So for this small model, it's not necessary. It actually is slower because you have to communicate the data to the GPU. The GPU runs it, data has to come back, but it's still a good practice now. So let's push the model to the device. And finally, we will come here now to the training function. So I define here a small function which takes a model, or optimizer, a data loader, and the loss module, all the components we have seen before, and then optimizes this model on the data given the optimizer and the loss module. The first part you have to do is you should set your model into the training mode. So PyTorch, each module has two modes, the training and the evaluation mode. This is because some modules actually have a different forward path, depending on if it's in training or if it's on evaluation. You will see in the lecture a few modules which actually have this component that they are quite different. Then we train here for a number of epochs. Here I say, for example, for 100 epochs. The data loader, now you see how you can actually use the data loader quite nicely in PyTorch. You just have a for loop for data input, save the labels in our data loader. For step one, we have to do push the data to our device, because if a model is on GPU, we also first have to push our data to GPU so we can run everything on GPU. Second step is then to take the inputs, push it through the model, and get a prediction out. We use the operation called squeeze. Squeeze basically removes then these components, so these dimensions actually which are 1. So the output actually is the batch size, comma 1, but we don't want the 1, we just want the batch size here. So that's why we use squeeze to remove this extra dimension. Finally, we perform, or we calculate then the loss. You can see here we put in the predictions, which are the logits, and the data labels, which we convert here. So originally the labels are long, right? So actually integers. While we do here .float means that we convert it into continuous numbers, because this loss module actually requires us to have continuous values. Step 4 is then, as we have previously said, we first remove all the gradients from the graph, then do the backpropagation with loss.backward, and finally take the loss.step, which updates the model. So now, after discussing the training function, we can finally run it and also start the training. You can see that it goes fairly quickly, and then finally you have a model which is optimized for the task. Of course, usually if you have then trained the model, one thing which is good to do is to save the model to the disk, because well, once you run the model, you don't want to forget the optimized parameters. You usually want to still store them and then do something with it later. In PyTorch, you can do it by saving the so-called state dict. So the state dict of the model, if we print it out here, is actually the parameters with their values in it. You can see here near weight, bias, all the tensors we had previously as a parameter. To save it, you can simply say torch.save the state dict, and then the file output, here I just call it our model.tar. Doesn't need any specific file extension. You can choose whichever you like. And then to finally load it, you can just use torch.load, which gives you the state dict, and then create, for example, a new model and call load state dict with the state dictionary, which then finally loads the parameters again into the model. Then we can see that we should actually have exactly the same parameter values as in this original model and this new model. So this way you can actually save it and load your model again. So now you have your model, you have trained it, but you of course want to know how good is this model actually? Does it generalize? For this, we should evaluate it, namely on a new test set, so on a held out test set. As our data set is really quite tiny, what we do is we create just a new test set and also a new data loader. We don't shuffle it, just as a good practice for the test and validation data. And we do here drop last equals false. Drop last means that if we, for example, after going through all the batches, the last batch is usually smaller than your indicated batch size because it depends on the training data size. and drop less during training, it's usually that you set it to 2 because you don't want to have tiny batches. But in evaluation and testing, it's important that every data is seen from your model. So drop less basically makes sure that really every single data point in the dataset will be shown as a batch. So let's run that as well. And we will use here the accuracy metric to evaluate our model. So that probably you already know, it's just the number of correct predictions divided by all predictions there are. We do now our evaluation. You see we first set the model to the evaluation mode. So as we discussed previously, the difference between training and evaluation is that some modules have a different forward pass for the two. We use here two, so we store here then number of correct predictions and overall examples. We'll use here a wrapper which is called with torch.noGrad. This one effectively tells PyTorch that it should not track this computation graph and therefore not track the gradients, because of the evaluation and test data set, we don't want to store the gradients or calculate the gradients because we just want to see the predictions, right? Therefore, this with torch.noGrad, it actually simplifies and also speeds up your evaluation. And then you can see we do basically nothing else as we have done in our training data. We put the data to device, predict then our output. Here now instead, as we had logics, we can first transform it using torch.sigmoid to a 0 to 1 output. And then we can just say predictions greater equals 0.5, which is when we're returning true if your prediction is greater than 0.5, otherwise false. And dot long converts it then into binaries or to longs between 0 and 1. Therefore, it gives you the predictions you want, and it's basically exactly the same notation as you would use in NumPy. We can then use here, just check which predictions are exactly with the labels, sum them, and then the number of predictions just with shape, of course, because this is the batch size here. The accuracy is then everything divided by numpreds. And if we train our model correctly, we should see an accuracy here close to 100%. This only because our training data is very simple. If you have harder tasks, we usually don't get 100% accuracy, unfortunately. As a last part, I just want to visualize the classification boundaries. So this number of 100% is quite nice to know, but we actually would like to know what did our model learn. And for that, I defined here a small function which visualizes it as in the figure we had all on top. You can see that actually with torch.noGrad, you can also use as a decorator for a function, which does nothing else than actually defines this with torch.noGrad for everything in this function. And we can run it. So there's now nothing new in it. And this actually shows you what the model has learned. And we see actually this quite nicely that we have here, the blue is all class 0 and separated the two classes quite well. With this, we basically then finish this tutorial. So we have seen how you can create now a model, how you can train it in PyTorch, optimize it. Of course, this is not the end. So there's a lot more to PyTorch, and we will discuss it then also along the different tutorials. We will discuss then what more functionality there is, what else you can try, and what is a good practice. But this tutorial should give you now a basis to start working in PyTorch, to start your assignment, and just know these basic concepts.